Modern GPUs can render more frames than ever before, but every extra frame now costs much more power than it used to. Years ago, increasing clock speed delivered clear performance gains with relatively small power increases. Today, that relationship is changing. Higher clock speeds require much higher voltage, while frame rates improve only slightly. The structural contradiction is simple. Performance keeps increasing. Efficiency no longer keeps pace. V1TA, data, retrieval, initializing core metrics. 4 variables explain this trend. First, frames per second. FPS measures how many images a GPU renders every second. Higher FPS means better performance, but not necessarily better efficiency. Second, power consumption. Every additional watt becomes heat that must be removed. Power is now one of the biggest limits in GPU design. Third, frames per watt. This measures how much performance each watt actually produces. As power rises faster than FPS, this number begins to fall. Fourth, operating voltage. Higher clock speeds require higher voltage to remain stable. Unfortunately, power increases much faster than voltage appears to. These 4 variables are no longer improving together. The problem begins inside the voltage-frequency curve. At lower clock speeds, GPU gains performance efficiently. Beyond a certain point, every extra MHC demands much more voltage. More voltage means much higher power consumption, but FPS only increases a little. The GPU starts spending far more energy for each additional frame. This is where frames per watt begins to decline. Modern GPU design avoids this trap. Instead of rendering every pixel directly, dedicated AI hardware reconstructs part of the final image. Tensor cores perform lightweight inference, while shader cores render fewer native pixels. The image remains visually similar, but total power grows much more slowly. Algorithmic reconstruction replaces electrical brute force. This trend is unlikely to reverse. Future GPUs cannot rely on higher clock speeds forever. Power density continues to increase. Cooling becomes more difficult. Electrical efficiency becomes harder to improve. As a result, future performance will come from different directions: better memory systems, smarter scheduling, AI reconstruction, more specialized hardware. Native rendering will remain important, but it will no longer be the only path toward higher performance. V1TA. Final assessment. Modern GPU efficiency is no longer defined by frequency alone. The industry is shifting away from electrical scaling toward algorithmic scaling. Future GPUs will generate more frames, not because silicon becomes dramatically faster, but because algorithms perform more of the work. Frames per second continue to rise. Frames per watt tell the real story.